Hello, welcome to Software Education. Today we will see some of the previous year UGC NET questions related to the operating system. See one of the questions which was asked in UGC NET November 2017 paper 2. The question here is that suppose there are 6 files F1, F2, F3, F4, F5, F6 with corresponding sizes 150 KB, 225 KB, 75 KB, 60 KB, 275 KB and 65 KB respectively. The files are to be stored on a sequential device in such a way that optimizes the access time. In what order should the files be stored? The four options are given 1, 2, 3 and 4. Here the question is asking about that to optimize the access time, in which order you have to be stored the files. Here to optimize the accessing time of the files, the order is that is depends on the size of the files. See here the F1 to F6 files are given as well as its corresponding sizes also be given, and observe the file which have the lower in size. So among the six files, the 60 KB file, that is maybe of the F4 file is the lowest size file, so that the F4 is the first file in a device to access. And second file is that after the 60 KB we have the 65 KB file, that is the F6 file, and after 65 KB file the next file is the 75 KB, that is the file number 3, and after that 75 KB we have the 150 KB file, so that is the F1 file, and after the 150 KB we have a 225 KB file, that is a F2 file, and after that you have the 275 KB of file which is related to the F5, right? So this is an order: F4, F6, F3, F1, F2 and F5. So that according to these four options, the option 1 is not the right one, and option 2 contains the files F4, F6, F3, F1, F2, F5. So that the answer for this question is a second option. Now so the next question, which is asked in the UGC NET November 2017 paper 2, which module gives control of the CPU to the process selected by the short-term scheduler? The options given here: the dispatcher, interrupt, schedulers and the threading. Among these four options, the right answer is the dispatcher, because of it is the definition of the dispatcher. Definition of dispatcher is that control the component of an operating system which gives the process to the CPU, which is selected by the short-term scheduler, is a dispatcher only. According to the textbook of Concepts of Operating System, in the chapter of a process, he has given the direct definition of the dispatchers, right? So here you have here the short-term schedulers is there, right? So in operating systems there are three types of schedulers are there. One is called as a long-term scheduler, one is called as the long-term scheduler, is also called as the job scheduler, and next one is called as the short-term scheduler, is also called as a CPU scheduler, and next one is called as the medium-term scheduler. It's called as a medium-term scheduler, right? So among these three schedulers, the job of the long-term scheduler is that to pick the jobs from the hard disk and put into the ready queue. This ready queue is available in the main memory of a computer. And the short-term schedulers which picks the jobs from the ready queue which is placed by the long-term scheduler, and the job picked from this ready queue and assigned to the CPU. And medium-term schedulers is the schedulers which can pick the jobs from the processor and swap into the swap space in a disk. After some time, and after the latter time, the medium-term schedulers picks the jobs from the swap space and again assign to the CPU, right? So in between of the short-term scheduler, are also called the CPU schedulers, we have an dispatcher. And after the dispatcher we have a CPU. So the dispatchers take the jobs from the short-term schedulers and assign to the CPU. So that the answer for this question is the first option, the dispatcher. And see the next question: the two atomic operations permissible on semaphores are dash and dash. So here the answer for this question is the wait and signal methods, right? So you know that one of the important topic in the operating system which was called as the critical section problem, right? So what is the meaning of critical section problem, right? Critical section problem, actually here what is a problem here? Critical section means it is a section where we store the shared data. The shared data may be of an hardware resources or it may be of an software resources, right? So in the critical sections we have to allow only one process to access the shared data, which doesn't allow the more than one process at a time to access the shared data. If you allow the more than one process to access the shared data, then what would be happen? Then the shared data can becomes the inconsistency. So to stop the processes, more than one processes, to stop the more than one processes to be enter in critical section, we have to use the sum of the mechanisms. We have the plenty of the mechanisms are there. One is called as the Peterson algorithm is there. Peterson algorithm is there, and then we have the Baker's algorithm is there, and then we have a semaphores are there, and then we have a monitors, and then we have a critical regions are there, right? So among these are the solutions of the critical section problem, right? These are the solutions of the critical section problems. Among these solutions, one of the solution is called as the semaphores. Yes, what is semaphore? Semaphore is an integer variable which is default initialize the value 1, which is default value is initialized to 1, and this semaphore variable values can be accessed by using the two atomic operations. One is called as a wait method, next one is a signal method. It is atomic operations. How we say it is an atomic operation? Atomic means it is not been divisible. It means that if one process is successfully executed the wait method, that same process has to be executed the signal method, then it is called as atomic operation, right? So that the answer for this question is called as a wait and signal. Now see the next question, which was asked in UGC November 2017 paper 3. Consider a virtual page reference string 7, 0, 1, 2, 0, 3, 0 and so on. Suppose a demand page virtual memory system running on a computer system such that the main memory has 3 page frames. Then dash page replacement algorithm has the minimum number of page faults, right? So this is a question related to the demand paging chapter, right? We have the set of page replacements algorithms. We have the FIFO and we have the LRU. We have an optimal is there, but the LIFO is not the one of the page replacement algorithm. Here the question is asking about that the CPU reference strings has been given here, as well as the number of frames is also given, that is the 3 frames are there. Now see the first we go with the FIFO, right? So if you take the FIFO, and what is the given string? The given string is 7, 0, 1 and so on is there. So he has given the 3 frames, 3 page frames is there. So initially all the page frames are empty. So whenever the CPU start its executions, it refers the first page, that is the page number 7. Page number 7 is not be available in this 3 frames, so that one page fault would be occurred. So that the 7 is to be bring into the main memory. And next is a 0 referred by the CPU. 0 is also be not available. We have the only 7 is there, so that the one more page fault would be occurred. So now up to we have the 2 page faults. And next page referred by the CPU is a 1. 1 is also be not be there. So that totally the 3 page faults are occurred here, right? And then next is the CPU referred the page number 2. Page number 2 is not be there, so that the one more page fault would be occurred here. Right here the question is that among these 3 pages, which page we have to be select as a victim page. So among this 701 we have to be choose the page which is to be arrived first in a main memory, because of it is an FIFO. So among these 3 pages the 7 is to be arrived first, so that in the place of 7 we have to write the 2, 0, 1. Next see the next page, that is an 0 referred by the CPU. The 0 is available, so that no page fault would be occurred. Next page referred by the CPU is the 3. 3 is not be there, so that the page fault would be occurred, right? So among these 3 pages, which page has to be selected as a victim page, right? So for this one we have to be choose the page which is to be arrived first in a frames, right? So that among the 201 the 0 is arrived first, so that in the place of 0 you have to be write the 3. And next to see the 0 is not be there, so that the page fault would be occurred, so that in the place of 1 we have to write the 0. And next page after the 0 there is a 4 referred by the CPU. The 4 is also be not be there, so that one more page fault would be occurred. Now we have to select the page which is to be arrived first in a main memory, so that among these 3 pages the 2 is arrived first, so that in the place of 2 we can be push the 4 3 0, and after that the CPU referred the 2 is not be there, so that we have to choose the 3 as a victim page. For in this one we have to write the 2, right, and 4 2 0. And next page referred by the CPU is a 3 also be not be there, so that the page fault would be occurred. So in the place of the 0 you have to be write the 3, and after 3 the CPU referred the 0 is also be not be there, so that in the place of the 0 you have to write the, in the place of 4 you have to write the 0, so 0 2 3. And next to that 3 referred by the CPU, 3 is there, no page fault. 2 referred by the CPU, 2 also already there, so that no page fault would be occurred. Next referred by the 1, CPU referred the 1 is not be there, so that page fault will be occurred. So that among these 3 pages the 2 is arrived first, so that in the place of 2 you have to write the 1. And after that the CPU referred the 2 is not be there, so that one more page fault would be occur. So that in the place of 3 you have to write the 2, 0 1 2. Next is CPU referred the 1 is there, no page fault will be occurred. Next the CPU referred the 7 is not be there, so that page fault will be occurred. So among these 3 pages the 0 is arrived first, so that in the place of 0 you have to write the 7, right, 7 1 2. Next page referred by the CPU is the 0, right, so 0 is not be there, so that the page fault will be occurred, and 1 is the arrived first, so that in the place of 1 you have to write the 0, 7 0 2. So now count how many number of the page faults. There was the 3 page faults as there, so 3 4 5 6 7 8 9 10 11 12 13 14 page faults are there by using the FIFO, right. So now see the next method. Next method, that is take the LRU, right. So LRU stands for the least recent use, right, least recent use. Recent use means that is on past references, right. So what is the main mechanism of the LRU is that, so among these references strings, there is a 701 203 and so on, 30 and so on. In this reference strings, LRU is saying that here we have to be take the recent past as an approximation of the near future. Then we will replace the page that has not been used for the longest period of time. So for example here, see at initially 701 is not be there, so that the 3 page faults would be occurred. And next page referred by the CPU is a 2 is not be there. So now among these 3 pages, which page we have to select as a victim? So by using the LRU is saying that we have to take the past references. So what is the recent use by the CPU, right? Among this 701, the CPU referred the page 1 recently, and then the 0 is referred by the CPU recently, and after the 0 and 1 7 is referred, so that we have to choose the 7 as a victim page. So that in the place of 7 we have to be write the new page that was called as the 2 0 1, so 2 0 1. Next page referred by the CPU is 0 is available, so that no page fault will be occurred. Next page referred by the CPU is 3, right, so 3 is not be there, so that the page fault would be occurred. Now which page we have to be choose as an victim page? So see the recent references by the CPU. Recently CPU referred the 0, so that 0 cannot be chosen as a victim page. Also the 2 is recently used, so the 2 is also not used as a victim page. And after that the 2 and 0 1 is referred by the CPU, so that 1 is selected as an victim page, right. So that 2 0 in the place of 1 you have to be write the 3. And next CPU referred the page number 0, right, 0 is available, so the no page will be occurred. Next page referred by the CPU is the 4, right, 4 is not be there, so that the page fault would be occurred. Now the question is that which page we have to be selected as a victim page. So that we have to see the previous references, right. So 0 and 3 is referred by the CPU recently than the 4, so than the 2, right? So that we have to choose the 2 as a victim page. In the place of 2 you have to write the 4 and then the 0 and then the 3 is there. And after that CPU referred the page number 2 is not be there, so that the page fault would be occurred. And see the past references, the 2 before the 2 the CPU referred the page 4 as well as 0, but 3 is last referred, so that in the place of 3 you have to write the page number 2, right? So that 4 0 2. Next page referred by the CPU is a 3, right? So 3, so 3 is not be there, so that the page fault would be occurred, so that we have to choose the which page here. So if you see here the 2 and 4 is recently used, so that we have to choose the 0 as a victim page, so that in the place of the 0 that is a 4 3 2. And next page referred by the CPU is a 0 is not be there, so that one more page fault would be occurred. If you see the past references by the CPU, so before the 0 you have a 3 as well as 2 is there, but the 4 is the longest, is a far is there, so that in the place of 4 you have to write the 0 0 3 2. And after that the CPU referred the 3, third page is also available, so that no page fault will be occurred. Next page referred by the CPU is the 2 is also be there, no page fault will be occurred. Next page referred by the CPU is the 1 is not be there, so that the page fault will be occurred. Now see the past references made by the CPU before the 1, the 2 and 3 is there, after the 0 is there, so that we have to be choose the 0 as a victim page. In the place of the 0 you have to write the 1, and next is the 1 3 2. And after that the CPU referred the page 2 already there, so that there is no page fault would be occurred. And next page referred by the CPU is a 0 is not be there, so that we have to perform the page replacement. See the previous references before the 0, 2 1 is there and 3 is the last one, so that in the place of 3 you have to write the 0, right? So 0 and then 2. And after the 0 the CPU referred the page 1 is there, so that no page fault would be occurred. Next the CPU referred the page number 7 is not be there, so that the page fault would be occurred. Now see the previous references before the 7 we have the 1 0, after that we have the 2, so that the 2 we have to choose as a victim page. In the place of 2 we have to write the 7. Now count what are the number of page faults. Initially there are 3 page faults, after that 1 1 1 is there, so that 3 4 5 6 7 8 4 5 6 7 8 9 10 11 12. There are 12 page faults are there. Choose the next mechanism, that is called as an optimal one, right? So initially there was 3 pages, so 3 page faults, so that for the 7 0 1 3 page faults. After that we had to be CP has to be referred the page number 2 is not be there, so that we have to be perform the page replacement. So how can we perform page replacement in optimal? That here we have to see the future references, right? We have to see the future references in this directions, so that after the 2, right? So after the 2 which pages the CPU has to be referred, right? So among these 3 pages 7 0 1, after the 2 the CPU referred the pages 0 and then 2 0 and then 2, and finally the CPU referred the page number 7, so that in the place of 7 you have to be write the 2, so 2 0 1, and after the 2 the CPU referred the page number 0 is available, so that no page replacement will be performed. Next is 3 referred by the CPU, 3 is not be there, so that we have to perform the page replacement. Among this 2 0 1 which page we have to be replaced, right? So for this one, see the future after the 3 the CPU referred what are the pages, right, among the 2 0 1. So after the 3 CPU referred the 0, so that we can only choose the 0 as a victim page, and then among the 2 and 1 2 is already there, and after the 0 and 2 the CPU referred the page 1 for the longest period of time, so that we have to choose the page 1 as a victim page, so that the 2 0 in the place of 1 you have to write the 3. Next page referred by the CPU is the 0 is there, so that no page replacement algorithm can be performed. And next one is the 4 is there, so 4 is not be there, so that page fault would be occurred. Now see the future references. After the 4, the CPU can refer the 2 and then 3. After that the CPU can refer the 0, so that among these 3, 1 0 is the longest usage, so that in the place of the 3 we can be write the page number 4, right? And after the 4, the next refer is the C2. 2 is already there, then so that there is no page fault. After that the CPU refer the page number 3 is there, so the page number 3 is not there, so that the page fault will be occurred. And say the future references. After the 3 we have the 0 is there, so that we can choose the 0 as a victim page. And after that 2 is there, so that we can choose the 2 as a victim page. And 4 is not be there, so that we can simply choose the 4 as a victim page, so that 2 0, and in the place of 4 we have to write the 3, 2 0 3. And after this the CPU referred the page 0. Page 0 is available, so that no page fault would be occurred. After that the CPU referred page number 3 is already there, no page fault would be occurred. And next the CPU referred page number 2 is already there, so that no page fault would be occurred. And next the CPU referred the page number 1 is not be there, so that the page fault would be occurred. And after the page 1 the CPU referred what are those pages among the 2 0 3. So after the 1 the CPU referred the 2 as well as the 0, but the 3 is not be referred by the CPU, so that in the place of 3 we have to write the 1. And after this 1 after this 1 the CPU referred page number 2 is already there, no page fault will be occurred, as well as 0 is also be there, 1 is also be there, and 7 is not be there, so that see the future references. After the 7 we have CPU refers the 0 and 1, so that we cannot be choose the 0 and 1 as the victim pages. So that in the place of the 2 we have to write the 7 7 0 1. Now count the how many page faults are there. Initially there are 3 page faults, and then 4 5 6 7 8 9, so totally 9 page faults are there, right? So that if you perform the minimum values among these 3 1, so 9 is minimum value, so that the answer for this question is the optimal page replacement algorithm. Now see the next question, which was asked in UGC NET November 2017 in a paper 3. He is asking about the it is a question about the threads. So in operating systems, what is a thread actually, right? A thread is a lightweight process, right? A thread is a lightweight process. It can perform the small or the simple activity or the operation of a process. A process can have the multiple operations, or these multiple operations can be performed by the help of the threads, right? So for example, take the word processor, right? The word process contains so many of operation. For example, the user can type the characters. These characters can be displayed on the monitors. It can be done by using one of the thread, or what you would type by using the keyboard. One dictionary would be open and checking the spellings, right? So this operation is to be performed by the another thread, right? And while the same time you can listen the audio also. So this thing is to be performed by the another thread of the process. So that to perform the multiple operations of a process, the process can be used the threads. In operating systems there are the 2 types of threads. One is called as a user level threads, next one is called as a kernel level threads are there. User threads can be created by using the user library, and kernel threads are to be created by the kernel itself. The information about the user level threads is doesn't known by the kernel, because of the information means what are the information? The information is about the threads, that is the how many threads are there, and what is the scheduling of the threads, what type of algorithm is used by the threads, and what is the management of the threads. So all these things cannot be known by the kernels, right? And kernel thread information is known by the kernel itself, because of it is created by the kernel, so that it knows all the entire information is about the kernel level threads, right? So some of the operating system, for example, take the POSIX threads, POSIX operating systems. In the POSIX operating system, the pre-threads library is used to create the user level threads, right? And for the kernel threads, the operating systems such as the Windows NT and Windows 2000 and OS bar 2 operating systems uses the kernel threads. And some of the operating systems such as the Windows NT and Windows 2000 uses the both types of the user level threads and the kernel level threads. When the operating system uses the both types of threads, that is the user level threads and the kernel level threads, at that time we can get the concept. That concept is called as a multi-threading models. That concept is called as a multi-threading models. So there are three types of models. One is called as the many to one, and next one is called as the one to one, and next one is called as the many to many. Next one is called as the many to many, right? So if you observe here, in this phrase, the first term is related to the user level threads. User level threads, and this second term is used for the kernel level threads. For the kernel threads. Okay. Now see, what is a many to one, what is a one to one, what is a many to many. Many to one means, so here we have the more than one user level threads, and for all these user level threads we have the only one kernel thread. And for the one to one means one for every user level thread there might be the one kernel level thread. And in the case of many to many, we have the many number of user level threads, as well as we have a less than or equal to the number of less than or equal to the kernel threads according to the user level threads, right? Now see the question here. He has given the question as a two parts. One is called as a A and next one is called as an B, right? So the many to one model maps many user threads to the one kernel threads. So many to one model maps the many users. Yes, right. So see the first word here, it is called as many. This many is related to the user threads, and this word is related to the kernel threads, right? So many user threads to one kernel thread, so that it is the right one. And next one is one to one. The first word is for the user, second word is for the kernel. So that maps the one user thread. Yes, it matches. This word is matches for this one, and this one is matches with this one. So that is also the right one. And this many is matches with the user level, and this one is maps the kernel level thread. So that a many to many model maps the many user threads to the smaller or equal kernel thread, so that this one is also be the right one. Now see the B options under this. Many to one models maps the many kernel threads to one user thread. It is wrong because of the first term must be matched with the user level threads, but here is given as a kernel thread, so that this option is wrong. And see the next one, one to one model maps the one kernel thread to one user thread. Is also wrong because of here the first word is maps to the kernel threads, so that it is a wrong one. And here also the many to model maps the many kernel threads to the smaller or equal user thread. This first term is here maps with the kernel thread, so that it is also a wrong one. Now see the options. Option 1, A is true, B is false. Yes, yes, it is right one because of A is true and the B is false. So that the answer for this question is the option 1. See the next question. This is a question related to the deadlock topics, right? So consider a system with 5 processes, P0 to P4 process. There are 5 processes are there, and there 3 resources types are there. Resource types, that is called as A, B and C, and A has 7 instances, B has 2 instances, and resource type C has 6 instances. At time t equal to 0, we have the following allocations, right? Here we have 5 processes, and we have allocations are there. That is allocations of resource types. So A, B, C are the resource types. And process P0, we had time t equal to 0, the system allocated the resources 0 of A instance, 0 of A instances, 1 of the B instances, and 0 of the C instances to the process P0. For the process P1, the system allocate the 2 instances of A and 0 instances of B and 0 instances of C to the process P1, and so on, right? And request, the future request of the process P0 is a 000, and P1 request, future request is the 2 instances of A, 0 instances of B and 2 instances of C, and the future request of the process P2 is 0 instances of all these resource types, and so on, right? Now at the same time the system have the resources 0, 0, 0, right? Now if you implement the deadlock detections algorithms, we claim that the system is whether the system is in semaphore, the system is deadlock state, surplus state, or not in deadlock state. So here among these 4 options, the first one is the wrong one, so that it doesn't be happen. The system can be in a deadlock, or it may be deadlock, or it may be in cycloped. That's all. But this one is not the answer. So this is the one of the topic related to the process synchronizations. Okay. See that whether by using this information, so whether it causes the deadlocks or not. So at present the CPU contains the resources 0, 0, 0. Right. Now what is the future request of the process P0? The future request of the process P0 is the 0, 0 instances. Right. So that if you write the sequence of the process, that is a P0 complete its executions, finish its executions. After the complete the execution of the process P0, it releases its allocated resources to the operating systems. So what are resources allocated to the process P0? That is the 0, 1, 0, and it is released to the operating system. Now the operating system has to be updated as previously it was 0, 0, and see process P0 release the resources 0, 1, 0. Now the CPU, now the OS contains the resources 0, 1, 0. Now the P0 completes its execution. Next to see the process P2 future request is the 0, 0, 0, so that the process P2 complete its execution and release the allocated resources. What are the allocated resources? The 3, 0, 3. Right. So that we can update the resources of the operating system as 3, 1, 3, 3, 1, 3. Right. So next request by the process P3 is 1, 0, 0. Right. So we have the resources 3, 1, 3, so that we can easily allocate the resources to the process P3, so that the next process completes the execution is the P3 process, so that I can add this P3 into the sequence. And P3 after successfully executions, it can release the allocated resources to the OS. What are the resources? That is called as an 2, 1, 1. Now the 5, 2, and here I have a 4. Right. Now the process, now the system contains the resources 5, 2, 4, and so that the P3 is also completed. Next the see the P4, the P4 request is 002, and the system contains the 5 to 4, so that we can easily allocate this resource to the process P4, and after that the P4 can complete its executions, it releases its resources to the OS. Now the OS can update its values 0, 2, 2. Now it have the 5, 4, 6. So, right. So next is the P4, and the 202 is requested by the process process P1, so that we can easily allocate it, so that the P1 is also become, so that here all the process can be successfully complete its execution, so that we can easily say that it does not cause any deadlock, so that the option 4 is the right one, that is a not in deadlock state. Now see the next question, the bounded buffer problem is also known as, right. So he has given the 4 options: producer consumer problem, reader separator problem, Dunning philosopher problem, both 2 and 3. So among these 4 options, the right answer is the producer consumer problem. Actually, what is a bounded buffer? Bounded buffer means under you know that there are 3 types of the classic problems of synchronizations. One is called as the producer consumer problem, next one is called as the Dunning philosopher problem, and next third one is called as the reader separator problem. Right. So here the producer consumer problem means there are 2 types of producer consumer problems. One is called as a bounded buffer, and next one is called as a unbounded buffer. Bounded buffer means here the buffer, assume that it is a buffer, and this buffer can be accessed by the 2 processes. One process is called as a producer process, and next process, the P2, is called as a consumer process. Right. The producer process can produce the new items and place into the buffer, and the consumer process is a process which can pick the items which is placed by the producer process, and it can consume the items. Right. And it is a bounded, means it is a bounded buffer. It is a bounded buffer. It means that here the size of this buffer is a fixed one. It may be a size is a 4 bytes or 10 bytes and so on. It is unbounded, means then this size is not be defined, so that is called as unbounded. Right. So that the answer for this question is called as a option number 1, producer consumer problem. Next, say the consider a system having m resources of same type. These resources are shared by the 3 processes P1, P2 and P3, which have peak demands of 2, 5 and 7 resources respectively. For what value of m deadlock will not occur? The options given here, the 70, 14, 13 and 7 is there, right? So for this type of questions, you can easily get the answers. That is, just you have to be count the demands of the three processes, that is a 2 plus 5, 5 plus 7, that is called as 14. So that the answer for this question is the 14. Next, see the one of the question which is asked in UGC NET August 2016 paper 2. Consider the CPU intensive processes P1, P2, P3 which requires a 20, 10 and 30 units of time arrive at 1, 3 and 7 respectively. Suppose operating system is implementing shortest remaining time first. It is called as a primitive scheduling algorithm. Then the dash, it means that it is the number of context switches are required. And suppose that the context switches at the beginning of ready queue and the end of ready queue are not be counted, right? So here what is the intention of this question is that we have to be perform the SRTF, that is a SJF, primitive SJF, right? Shortest job first scheduling. So he has given the processes, right? So what are the processes? The processes are the P1 process and then the P2 process and then the P3 process. And what is the CPU burst times? In the CPU burst times he has given that for the process P1 the 20 and it is in 10 and it is for the 30. And what is the arrival time? Arrival time he has given that 1, 3 and 7, right? So now see the Gantt chart of this processes. At time t equal to 0, none of the process can be arrived. At time t equal to 1, the process P1 is to be arrived and process P1 is to be arrived. At time t equal to 3, the process P2 is arrived, right? Process time t equal to 3. At time t equal to 3, already the process P1 complete its execution up to the 2 milliseconds. So that next is the 18 is there. 18 is there and the process P2 CPU burst time is the 10. So that among the values of 18 and 10, 10 is the smallest value, so that we can schedule the process P2 to the processor. And at the time t equal to 7, the process P3 has been arrived in a ready queue with the CPU burst time is the 30, right? So it means that at this time of time t equal to 7, the process P2 already executed up to the 4 milliseconds. So that here the 10 minus 4 is 7. So if you compare the 7 and 30, the 7 is the minimum value, so that again the P2 would be start continue its execution, right? So that it can be successfully complete its execution up to the 10, so that here you can get the 13, right? So now the P2 has completed execution. Now we have the P1 and P3. P1 time CPU burst time is 18 and the P3 CPU burst time is the 30. So among the 18 and 13, 18 is the smallest time, so that we can be allows the P1 process to complete its execution, right? So that the 13 plus 18 is a 31. At this 31 milliseconds we can schedule the process P3, right? Now see what are the context switching here. So there is a context switch from P1 to P2 and here there is no context switch, and P2 to P1 there is a context switch, and then the P1 to P3 is an context switching, right? So that there are 3 context switchings out there, so that the answer for this question is the option number 1. And see the one more question which was related to the page replacement algorithms. Consider the following page references strings 1, 2, 3, 4 and so on he has given, and which of the following options gives the correct number of page faults related to the LRU, FIFO, optimal page replacements algorithm respectively, assuming the 5 page frames are there and all frames are initially empty, right? He has given the 5, initially all these 5 frames are empty, right? All are empty. And see the 5 frames for these 5 frames. So he has given the 5 free frames. Initially all the 5 free frames are empty, okay? So first take the first page replacement marker has given the LRU. Right, so assume that is an LRU, least recent use. It means that we have to see the previous references of the pages by the CPU, right? So initially 1, 2, 3, 4, right? So 1 is not be there, so the one page fault will be occurred. Next the page 2 referred by the CPU, 2 is also not be there, so the second page fault will be occurred. Next page referred by the CPU is the 3, 3 is also not be occurred. No, the third page fault, 4 is also be not there, so 4 page faults, and 2 is already there, no page fault. 1 is already there, so that no page fault. 5, for the 5 the page fault would be occurred, so that initially you have to get the how many page faults, the 5 page faults are there. Next the CPU referred the page 6. The page 6 is not be in the 5 frames, so that we have to be choose the one of the page as a victim page. So under the LRU we have to see the previous references of pages by the CPU. So before the 6 the CPU referred the 5, so that we cannot be choose the 5 as a victim page. After that the 1 we cannot be choose the 1 as a victim page, and 2 is there, 4 is there, and then the 3 is there. So that among this one, so that we can choose the 3 as a victim page. So that in the place of 3 I can write the 6 and then 4 and then the 5. After that CPU referred the page number 2, 2 is there, so that no page fault will be occurred. CPU referred the page 1, already there, no page fault will be occurred. 2, no page fault will be occurred. 3 for the 3 the page fault will be occurred. And for this one we have to see the previous references before the 3 made by the CPU. 2 is referred by the CPU, so that we cannot choose the 2 as a victim page. 1 we cannot be choose, and 6 we cannot be choose. 5, after that 4, so that in the place of 4, right, so 1, 2, 6, in the place of 4 you have to write the 3 and then the 5, right? And after that the CPU referred the page number 7, so 7 is not be there, so that page fault would be occurred. Now we have to see the previous references before the 7 made by the CPU, right? So 3 is referred recently, so that we can only choose as victim page, and 2 is 2, and then 1, and then 6, and then 5 is there, and then the 3, right? So 3 is there, and then 2 is there, right? So 1 is there, 6 is there, right? So that we have to choose the 5 as a victim page. So 1, 2, 6, 3, and in the place of 5 we have to write the 7. Next page referred by the CPU is the 6, 6 is there, no page will be occurred. 3 is referred, 3 is also be there, no page will be occurred. 2 is there, 1 is there, 2 is there, 3 is there, 6 is there. So that how many page faults? So 5 plus 1, 6, 7, 8, 8 page faults. 8. Now see the next page replacement algorithm, which is called as an F5 F4. Right, so here again we have the same 5 free frames. Right, so initially we have get the 5 page faults for the pages referred by the CPU, that is the 1, 2, 3, 4, 5 page faults. And after that the CPU referred the page number 6, 6 is not there, so that page fault will be occurred. So that among these 5 pages, which page has to be selected as a victim page? We have been following the page replacement, that is an F5 It means that the page which is to be added first in this memory, that page will be selected as a victim page. So that among these 5 pages the page 1 has been added first in a memory, so that we have to choose the 1 as a victim page. In this place of 1 we can be write the 6, 2, 3, 4, and then 5. After that the CPU referred the page 2, page 2 is there, no page would be occurred. 1 is not be there, so that the page fault would be occurred. And among these 5 pages the 2 is arrived first in a memory, so that in the place of 2 you have to write the 1, 6, 1, 3, 4, 5. And after that the CPU referred the page 2, 2 is not be there, so that the page fault would be occurred. Among these 5 pages 3 is arrived first, so that in the place of 3 you have to write the 2, 4, and then the 5. Next page referred by the CPU is the 3, 3 is not be there, so that the page fault would be occurred. And among these 5 pages the 4 is arrived first, so that in the place of 4, that is a 6, 1, 2, in the place of 4 we had to be write the 3 and then the 5. Our next page referred by the CPU is the 7. 7 is not be there, the page fault would be occurred, and we have to choose the 5 as the victim page because of it is errored first among the remaining pages. So that's 6, 1, 2, 3, and in the place of 5 we have to write the 7. Next, CPU referred the page 6. 6 is there, no page will be occurred. 3 referred by the CPU, no page will be occurred because of it is available in a main memory. And 2 is referred, is also available, no page fault will be occurred. 1, no page will be occurred because of it is available. And 2 is also available, no page will be occurred. 3 is available, and 6 is available. Right. So that how many page faults? By default, here we have the 5 page faults. So 5, 6, 5 page faults. So initially we have the 5 page faults here, 5, and then the each one page faults here, so that 2, 5, 6, 7, 8, 9, 10 page faults are there, right? And see the next one, that is called as optimal page replacement, right? So what is an optimal page replacement here? The optimal means, so here we have to see the future references of the pages referred by the CPU, right? So take the same reference string here. Initially we have to get the 5 page faults, so that is called as 1, 2, 3, 4 and 5 page faults, so that here the 5 page faults are there, right? And after that the 6 is referred by the CPU, the 6 is not be there, so that the page fault would be occurred. Now we have to check that which page we have to be select as a victim page, which page we have to select as a victim page, right? So for this one, see the future references. After the 6, the CPU refer which pages. After 6, the CPU refers the 2 and then 1 and then the 3 and then the 4 and 5 is not be referred in a future, so that among this 4 and 5 we can choose the 4 as a victim page. 1, 2, 3, I am choosing the 4 as a victim page, so that in the place of 4 I am writing the 6 and then the 5 is there. Our next page referred by the CPU is 2, right? So that here next page referred by the CPU is the 2, right? So 2 is there, so that no page fault would be occurred. Next page referred by the CPU is the 1 is there, so that no page fault would be occurred. Next page referred by the CPU 2 is there, no page fault would be occurred. 3 is there, and next page referred by the CPU is the 7, right? 7 is not be there, so that the page fault would be occurred. So that among these 5 pages, which page you have to be select as a victim page. For this one, see the future references after the 7, that is 6, 3 and 2 and 1. 5 is not be referred in the future, so that we have to choose the 5 as a victim page, so that 1, 2, 3, 6 in the place of 5 we have to write the 7. And after 7, the CPU referred the 6. 6 is available in a main memory, so that no page fault would be occurred. 3 is also be there, 2 is also be there, 1 is also be there, 2 is also be there, 3 is also be there, and 6 is also be there. Now how many page faults are there? So initially 5 page faults, after that 1, 1, so that 5 plus 1 becomes the total 7. So that how many page faults? For the LRU is a 8 page faults, for the LRU 8 page faults, and for the FIFO 10 page faults, and for the optimal 7 page faults. So that 8, 10, 7, the answer for this question is the option number 2.